Time for revision again. Okay, so let's continue with thermometry. It's a simple thing, and this is a question which have come. And let's see if you visualize this figure. The reason I have given this figure, if you get a mental picture of what happens, the understanding of formula, there's no need to memorize. So this is thermometer graduated according to linear scale. So this is a arbitrary February. So not this is Kelvin, this is X scale here. And what it says here, a thermometer graduated according to linear scale. It reads a value of X naught when in contact with the boiling water. So now, so what happens? Centigrade scale will read 100 degree, but this is not reading 100 degree. It is reading it is having a reading of X naught, and it has a reading of X naught by 3 when contact with ice. This reading is X naught by 3. And what is the corresponding reading? So any other scale, this is kind of reading we would have. So basically heights are same. What is the temperature in degrees centigrade if this thermometer is in contact with the object which reads X naught by 2? So here, this is the reading I want to find out. This is reading it when it is brought in contact with some object, and it reads X naught by 2. What is the corresponding centigrade reading? So centigrade reading will be equal to this difference by this difference will be equal to this difference divided by this difference. And how do we write this one? Centigrade reading will be equal to centigrade reading minus lower fixed point divided by upper fixed point divided by lower minus lower fixed point. So I have corrected that part, RC minus lower fixed point. And similar way I do for other scale also. Let me just substitute those values. So which are the two? One side I'm substituting X scale reading, other side I'm substituting centigrade reading. Here X naught by 2 minus X naught by 3 divided by X naught minus X naught by 3. Correspondingly here also this reading is centigrade reading C minus 0 divided by 100 minus 0. It will give value of C here. That's how we use this conversion. And this kind of any question, any kind of whatever values are given, we can easily solve. Another similar question, this also is a question which has come, an extremely simple question. A constant pressure air thermometer, it reads 47.5 units. And these units are not important, the ratios are, we use ratio only of volume. So constant pressure, here pressure is constant, hence volume is proportional to temperature when immersed in ice cold water. And when it reads 67 units in boiling liquid. If it reads 65 reading in a boiling liquid, it is not necessarily water. So what is the boiling point of the liquid? That's what we need to find. How do you find boiling point and which principle we use here? So as pressure is constant pressure, volume is proportional to temperature in Kelvin. That is important here. We cannot use any other scale here. It is proportional to T in Kelvin. And then in that case, very simple, we can easily write that equation. V2 by V1 is equal to T2 by T1. Very simple. And we get the temperature. Okay. Similar to this one, we come to topic of calorimetry. Calorimetry is basically it measures heat flow. So, and what is energy here? See, we have come across different forms of energy. Heat also is a form of energy. And one way to understand heat energy, we in case of linear motion, we talk about any object if we keep on a surface, and if object is moving on a rough surface, what do you say after some time it comes to stop? We say mechanical energy is lost. And mechanical energy is lost, but where it has gone. So some of it may go in form of heat energy also. So heat energy, and when we talk about heat energy, understanding heat energy, see, we know if we bring any two objects in contact, thermal contact, if there is a difference in temperature, heat will flow. So heat is what? Heat is one way to understand. Heat is a form of energy which moves from higher temperature to lower temperature. It's a means to transfer energy from one object to other object. And that's why it is called is energy in transit. Heat is when temperature difference exists. And what is the effect of heat energy? Object is there. If we give heat energy or remove heat energy, what are the different effects, physical effect it produces. So one of the effect we have already studied. If we heat up an object, basically heat up means what? We are supplying heat energy. If we cool an object, we are taking away heat energy. In that case, one we have understood is change in dimensions, which we have done thermal expansion and contraction. That's one effect. What are other two effects? See, other effect is change in phase or change in temperature. So change in temperature. So when you heat up water, you notice here when you put up some water on a kettle, initially what will happen, the temperature will keep changing, phase will not change, but after some time you say the water will start evaporating, and that is change in phase. So these are three effects. One we have done. Now this part we'll do this part, these two things. So whenever heat is given, so heat given is related to change in temperature. So what is the relationship? And change in temperature we can relate in three different ways. We'll deal with one by one. Heat is equal to, can be written as heat given to an object, can be related by this equation mc delta theta. And this itself, it gives you value of C. What is C here? C is specific heat capacity. C is specific heat capacity. And unit itself is, if you understand what is specific heat capacity. Specific heat capacity is amount of heat required to raise the temperature of an object of unit mass by 1 degree of whichever scale we use. 1 degree centigrade, 1 degree Fahrenheit, or 1 degree Kelvin. That's a specific heat capacity. Specific heat capacity we use normally for solids and liquid. Whereas when we, in case of gas, we have similar equation, but rather than mass of the object, their number of moles become more important. So we use, in case of gas, Q is equal to NC delta T or delta theta. So we'll use this term. You always be in mind, we'll use this term delta theta and delta T interchangeably. So, but this is molar heat capacity. The one is specific heat capacity. This is per unit mass. This is per unit mole. And when we multiply M and C together, it is called heat capacity. Heat capacity of an object is equal to M into C. And naturally, heat capacity in an object is not the property of the material. It reflects the property of the material as well as mass of the object. So there are three different heat capacity, and depending on how temperature and heat is related, Q and delta theta, change in temperature related in this fashion. So in terms of mass, mc delta T, nc delta T, and c delta T or delta theta. For water, so yes, this is heat capacity is equal to 1 calorie per gram per degree centigrade. And in terms of SI unit is basically heat and mechanical energy. See here, the friction can be converted into heat energy. So they are interchangeable. So there are two different forms of energy. So calorie is we use for heat energy, but it doesn't mean the calorie also is a unit of energy. So if calorie is a unit of energy and joules also is energy of unit of energy, we can convert one from other, and they are interchangeable. So 1 calorie is where we should remember that conversion. 1 calorie is equal to 4.18 joules or 4.2 joules. I think most of you remember that. And we use same cases of conversion. So when we convert, we can also write it. This C is equal to calorie. Yeah, so we substitute, it becomes 4.2 kilojoules kg per degree centigrade. And specific heat capacity of ice is half. So what do you understand? Specific heat capacity of ice is half. So it means if I have equal mass of ice and water, amount of heat I need to raise the temperature of water by 1 degree, for same mass of ice, I will need only half the energy. Or other way of saying, if both are equal mass, if they are given same amount of heat, temperature of ice will rise by twice as much. The heat capacity is half. And then second thing, that's one effect. So we dealt with effect of change in temperature. This is a relationship, heat energy and temperature. Second is latent heat. Latent heat, when we keep supplying heat and the temperature does not change. So if the temperature does not change, yes, of course, the natural question is where does that energy go? That energy goes into change of phase, and that may be from solid to liquid or liquid to gaseous form. So change in phase without any change in temperature. In that case, relationship is Q is equal to ml. So these are only two things we are going to use in this chapter, this subtopic here. Q is equal to MC delta T, and Q is equal to ML. There's no temperature. Mass is amount of heat is given. This is the mass which undergoes change of phase. M indicates change, mass which undergoes change of phase. And the two different kinds of transition. One transition is latent out of fusion, which is from solid to liquid, and both ways it is same. So what amount of heat you need to give to ice to melt, and again for same water which is ice which is melt, again you want to again solidify, same amount of heat need to be taken away. So both ways it is same. And this is a latent heat of evaporation, 540 heat required to evaporate each a gram of water. So what we notice from here, amount of heat required to evaporate 1 gram of water is 5.4 times the heat required to raise the temperature from 0 to 100. So if I have to raise from 0 to 100, each degree 1 calorie, if I take 1 gram of water, so for 100 grams, I need, for 1 gram temperature to be raised from 0 to 100 calories required. But just to convert that 1 gram from 100-degree water to steam at 100 degree, amount of heat required is 540. So that's why you notice here, amount of heat required for vaporization is much larger than the heat required for heating. That's why when you put a vessel on the heater, you say the heating will take less time, but if you want to evaporate whole water, it will take more time. It takes more energy. And we also talk about water equivalent. I'll come to some equation. If we, any two objects we have, so one side we have some mass of water, and another side we have some other object here. Some object, it has mass M. It has heat capacity C. This is heat capacity, specific heat capacity CW. What does a basically calorimetric equivalence mean? If they have equal heat capacity, if heat capacities are equal, same amount of heat given, the change in temperature also will be equal. So when we take water equivalent of object, this is the equation we use for water equivalent. So how much mass of water is equivalent to a given mass of object having a specific capacity C. So MW will be equal to MC by CW, which I'll use, which we'll use in some of the questions. To understand, let's see that one, a temperature time graph. So what does this graph indicate? So suppose we have a heater, and we start with in a vessel or in a thermally isolated case. We take a case here, and this we take some certain amount of ice, which is initially at minus 50 degrees, super cooled ice, minus 50 degrees centigrade, and we start supplying heat at a constant rate. So power is same. And power could be in form of a heater also. This is some heater, and when we observe, and in this case what we observe here, we heat in a such a way that temperature all across remains the same. So temperature mixing is so efficient, or heat is supplied so slowly, that every part of this object is at the same temperature. So and it will happen only when the conduction is high or mixing is so good. So if we supply heat and we plot time against temperature, this is the graph we get, and we understand this graph is critical to understanding calorimetry. When you supply heat, what we find here, see, it takes some time t for temperature to rise from here. We continuously find the temperature is increasing in the linear fashion. For minus 50, it is keep increasing in the linear fashion. So it has taken certain time t the temperature to rise from minus 50 to 0. After it reaches 0, what we find, even though we keep supplying heat, and every time we have a thermometer keeps showing continuous record of the temperature, we find the temperature does not change. Only thing what we find, if you look in the vessel, we slowly find the ice is gradually converting into water at 0 degree centigrade. So this melting will take place. For certain time, we know the temperature remains constant. And afterwards, again, I find here, we keep checking here, the temperature will keep rising. And what I notice here, this slope of these two curves are not equal. Okay, we'll see that part also. And it increases in linear fashion. It will happen in the linear fashion even if only if the heat capacity of water is constant at different temperature. We assume heat capacity of water to be constant at different temperature. And at 100 degree, again, we find we keep supplying heat for a long time, and we find the temperature remains constant at 100. And this is something, so here, whatever heat we have supplied, this part of the heat has gone as a latent heat for fusion, and here it is latent heat of evaporation. After that is turned into uh, steam here. Let's understand this heat supply and constant rate, assume the temperature is uniform all across the mass, time intervals and slope. What we need to understand, if this has taken time t, then what will be time taken from here to here in terms of t? We can express all this time in terms of multiple of t. T being the time taken from where to where, t taken the time from temperature to rise from -50 to 0. So we have to understand the first part. Let's understand what does PT mean. So if power supply, power is P, heat supplied in time T is equal to PT, and PT will be equal to, it is, sorry, PT will be equal to MC delta theta. And which C we need to take? Specific heat capacity. In this phase, it is ice. So I have to take specific heat capacity of ice, which is 0.5. So this one I need to write P in time T is equal to 0.5. Sorry, mass into 0.5 into 50. Okay. So that's the amount of heat which is supplied from this time to this time. Amount of heat supplied is equal to 25 M. And M is in grams. And then only this will be in terms of calorie here. This is the heat supplied here from 0 to T. Now think of what is the heat I need to supply from here to here. Can you all easily think what is the heat supplied from here to here? Amount of heat. So first we have calculated Q1 here. Q1 is equal to this term 25 M. From here to here, since the latent heat is 80, if there are m grams of water, it will need 80 m amount of energy. And how much time? 80 amount of so PT is equal to, let's look at this. Okay, so this amount of heat required, this compared to Q1 amount of heat required, here heat required per gram was 25, here heat required to completely melt this per gram is 80, hence this will be equal to 3.2 times. So if this time is t, this will be 3.2 t. And from here, why the slope changes here? See, for same amount of heat supplied here, specific heat capacity was 0.5. Now the specific heat capacity becomes 1. Since the specific heat capacity becomes twice, it needs twice as much of heat energy for same change in temperature. That's why it takes double the time. Slope here is half of the slope here. This slope will be half of the slope here. And we can easily calculate. How do we calculate here? If the slope here, in case of this part, P into dt is equal to M into 0.5 delta theta. And here if I write P into dt, heat supplied in time delta t will be equal to M into 1 into delta theta. So what is delta theta by t here? The slope becomes half here. And what does this indicate here? So we can easily calculate. So understand the ratio. I'm not explaining again all those things here. If this is t, this will be 3.2 t. This will be 4t, and this will be 21.6 times t. So whatever time it has taken to just raise the temperature from -50 to 0 degree ice, from 0 degree ice to 0 degree water, it will take 3.2 times more time, and so on and so forth. Okay. So total heat required. So let's understand, and this figure is key to understanding calorimetry here. So let's understand some more. Total heat required to heat m grams of ice at -50 degrees centigrade to steam at 100 degrees centigrade. What is the total heat required? So just understand here. The total heat required is heat given here, plus heat given here, plus heat given here, plus heat given here. What is this equal to? Here to convert -50 degree ice to 0 degree ice, then 0 degree ice to 0 degree water, then 0 degree water to 100 degree water, and then 100 degree water to 100 degree steam. And that's what you should know how to calculate here. If m grams, so this amount of heat will be equal to m into 0.5 into 50, first step, plus m into 80. This is up to 0 degree water, sorry, 0 degree ice. Then this is 0 degree ice to 0 degree water, plus m into 1 into 100. This is this part of heat, plus m into 540. So this is figure you should have in mind. But this is why all question, if we understand what are the, how do I calculate heat required for, or it go to from one point to other, we should know. this is kind of heat required. Okay. Then what are other point that says so far we only related heat required to change in temperature and change in phase. Second part is what happens in principle of calorimetry when thermally isolated objects at different temperatures are brought together. The heat transfer takes place until common temperature is reached. This is very common understanding. And for an isolated system, basically if we take up a thermocouple, if we take a system where heat is not being received, not being lost here. If two objects are brought together, the object which was at higher temperature, it will lose heat energy, and object which is a lower temperature will gain heat energy so as to reach a common temperature. And this is the equation what we use here. So loss of heat energy is equal to gain of heat energy. So when we write calorimetry equation, so this mass m, which is giving mc, this is object which is higher temperature. Higher temperature will lose heat energy. So here we started theta h minus theta naught. Theta naught is the final temperature, and here this will gain heat. So basically, final temperature is higher than initial temperature. Just notice how do we substitute here. So this is something in case of loss, the final temperature will come after. In terms of gain, the final temperature will come first. Plus ml if any change in phase is involved. That's a calorimetry equation we are going to use. Let's apply in some cases here. And this is common, you understand here. If you have two liquids in two different cups, and if the liquids are different temperature, if you mix them, it will reach to a temperature which will be somewhere between the two. It will not necessarily be mean temperature, but it has to be, if you mix two things, it will be higher than the lower temperature and lower than the higher object's temperature. Let's see in this case. So temperature equal masses of three different liquids. We have taken three different liquids, A, B, C, and they are at temperature 12 degree, 19 degree, and 28 degree. When A and B are mixed together, it results in temperature of 16 degree. When B and C are mixed together, it results in temperature of 23 degree. And what is the temperature when A and C are mixed? That's our question. So all such questions, moment to spot is calorimetric question, is equal to heat gain is equal to heat loss kind of question. Let's see when A and B are mixed here. So A is at 12 degree, B is 19 degree. A will gain heat and B will lose heat. The energy lost by B is equal to heat energy gained by A. And we should be easily write this equation. M into CB, masses are equal, all have equal masses, M values are same. And specific heat capacity of different liquids are not same. So MCB, so if B is losing heat, 19 minus 16 final temperature. Similar way I can write this equation. This is very easy equations to write. And similarly, when B and C are mixed, when B and C are mixed, again we can write a similar equation. So we get these two equations here. And then what we need to find? We need to find what happens when A and C are mixed together. When A and C are mixed together, the C will lose heat, AC, and let theta be the common temperature. This is what we need to find here. And to find, I can substitute basically, we need to find ratio of Cc by Ca to find this equation. And ratio of specific heat capacity or liquid C and A can be found from first two equation. From first two equation, I find the ratio of specific heat capacity of two liquids. I substitute it here. I can find the value of common temperature they will reach after mixing. Okay, and this question, if you this is something I have done in three parts. If all parts you understand, I think the major part of calorimetry is done. So X gram of ice at minus 20 degrees centigrade is added to 10 grams of water, and water is at 60 degree. Okay, and now we find what is F. Let's put different parts here. So what is this value of X? Basically what we are saying, how many grams of ice at minus 20 degree should be added to 10 grams of water so that final temperature is 0, but it does not contain any ice. No ice is left. Okay, and this no ice is left, and this is something unlike. Don't try to relate it to your putting ice in a glass of water. Because in case of glass of water, what we do, there's a constant loss of heat energy is taking place. If you have to visualize this question, just imagine that glass of water, having a glass of water, and in this case, glass should have negligible heat capacity. It should not absorb water heat itself. And if we did, if we ice here, if we add some ice here, how much ice quantity I need to add so that like this. See, if I have to visualize this question, so we have two things here. See, what are two things here? There's ice here at minus 20 degrees centigrade. And just see where is water here on this graph here. Where's the water here? Water is at 60 degree. This is 0 degree, this water here. You know, so when we mix these two together, final state can be any of these things. Final state could be A also, it could be B also, it could be C also, it could be D also, and it could be E also. What does A imply? What does state E means? Well, basically, when would A come? When I add lot of ice comparative to, if ice quantity is lot more than mass of water, the final temperature will be closer to this. What would state A mean? State A means entire thing is ice. Entire thing is ice and still at temperature less than 0 degree. Do you think, just see what will happen? And what does state B imply here? B implies entire thing is ice at 0 degree. Entire ice at 0 degree. So if this is something as value of x keeps decreasing, if x is very large and x keeps decreasing, the final state will keep shifting towards right hand side. And what does C state imply here? Can tell me someone what does C state mean here? Anish, can you tell me what does C mean here? Can you think of what does point C indicate here? Okay, a lot of distance coming. Okay. What does C here? Let me ask someone else then. Vikram, can you tell me what does C mean here? What does C mean here? What does point C indicate? What does B indicate and what does D indicate? Let me write D also. What does point D indicate here? D indicate entire thing is water. At what temperature? At 0 degrees centigrade. So as I keep increasing, as I keep decreasing x, and what does point E indicate? Entire thing is water at more than 0 degrees centigrade. And do you understand? Does it make logical sense here? As x keeps decreasing, the final state may come in something like this. And depending on which state is coming, you will have a different equation. And that's why some of the questions which are a little more tricky, you cannot have a unique equation and get an answer. You need to assume, okay, what is my final state? Either the question itself tells you, if the question tells you, find the mix of, what does C indicate? C indicates part water, part ice. C indicates it is still at 0 degree, but entire thing is not melt, entire thing is not ice. Part water, part ice. Okay, so first thing you need to figure out which state it is in. If it is state A, it means how much energy water at 60 degrees is lost. Water has first converted into water at 0 degree. Then it has converted ice at 0 degree. And then further it has cooled down to ice at temperature less than 0 degree. And that's how we need to write equation. So is this figure making some sense, Shreya? Is this figure making some sense to you?
Yes, sir.
You understood what does point C mean?
Yes, sir, I understood.
Understood. And once we figure out where it is, so this is something, if I figure out the point here, then I can calculate, okay, this is the amount of heat gained and this is the amount of heat lost. And then I need to take appropriate steps also. The heat loss, if final state is ice at less than 0 degrees centigrade, it will have loss of energy. This step plus this step plus this step. All those things have to be correctly written here. So if the final temperature is 0 degrees centigrade, but no ice left, it means it is point D. So how do I write equation here? Entire x from ice is first it has turned into ice. So heat gained by ice is from this step to this step, then from this step to this step. The equation will be x into specific heat capacity of ice, change in temperature from 0 to 20. So I could have written directly 0 minus 20 because we started from 20. So I could have written x into ice into 20 plus x into 80. Thus the amount of heat it has gained, and heat lost by water at 60 degree, it has lost temperature 60 degree. So m into 60. I can calculate x here. Second part, if final temperature is 0 degree with no water, how would my equation change? No water means what? The ice, this is the state here. This is the final state. In that case, equation, if entire x gram of ice has turned into ice at 0 degree, whereas 10 grams of water has lost heat first to turn into water at 0 degree and then formed into ice. So how do my equation will be? The equation, this is the heat gained by ice here. Delta T is equal to 20 degree, and water 10 into 60. This is called sensible heat plus the latent heat also. I can calculate. So in 10 grams of water, if I add 140 grams of ice at minus 20 degrees centigrade, I'll be left with 150 grams of ice at 0 degrees centigrade. That's what it means. And third is question is something in between, neither this or not this. If I add a quantity of ice which is greater than this but less than this, if 100 grams of ice is added, what will the final temperature and amount of ice? When this is, we have done these two parts. So now we understand here, it will lead to state C. It will be partly ice and partly water. What is final temperature and amount of ice? The moment wording is there, final temperature and amount of ice, it gives me a hint that final state is a mix of water and ice. And whenever a mix of water and ice exists, final temperature must be 0 degrees centigrade. Okay. Assuming if I do that one, so, okay, so let's suppose we make assumption. We start with assumption that a part of ice has melt. Okay, the final state, part of ice has melt. I assume the x gram of ice has melt. So in that case, how would I write my equation? So final state contains mix of ice and water. So this way. If x gram of ice is melt, it means 100 grams of ice at 20 degree. First, it has gained heat to rise to 0 degree. Plus only part, not 100 grams. X gram has melt, so x into 80. This is the amount of heat gained by ice. And since the final temperature is 0 degree, the heat lost by 10 grams of water is 10 into 60. But when I solve this equation, I get x equal to minus 5. What does x equal to minus 5 mean here? And that's what will happen. We assume something, and I get from this equation, you can simplify. You get x is equal to minus 5. What does this minus 5 mean? Minus 5 is that the ice will not melt. On the contrary, 5 grams of water will solidify into ice. That's what it means. So final mix, even 10 grams also, so it means my assumption was wrong. The ice will not melt. Either I can rewrite the equation or I can interpret minus 5 grams means how much ice minus 5 grams melt means rather than 5 grams melting, another 5 grams has solidified. So what would final mix indicate here? The final mix will contain 105 grams of ice plus 5 grams of water. Or I could have written a second equation. What is second equation? I would have written a second equation, assuming that x gram of water has solidified into ice. And the final temperature at 0 degrees centigrade. In that case, what would have been equation? The equation would have been, so just see what the equation would be. The equation would be 100 into specific capacity of ice into 20. Thus, heat gained by ice and heat lost by water would be 10 into 60 plus x into 80, which is same equation. This has gone to this side. That's all. So I hope this part is understood. Dhanshri, are you following this?
Yes, I am.
This figure you understood somewhere?
Yes, sir, the figure is clearly understood.
Yeah, okay. Okay, so this is the only tricky part in calorimetry. Otherwise, absolutely nothing. We just form equation and get an answer. Okay, let's look at some more numericals based on this. 2 liters of water, initial temperature is heated by heater or power so and so. If the lid of a kettle is open, then heat is lost at the constant rate. And this is typically what happens. Whenever you heat any object, the heater supplies some amount of energy and some power in the unit time, and some of it is lost to the atmosphere. Then what is the time required to raise the temperature of water to 77 degrees centigrade with lid open? Okay, a specific heat of water is given, everything given SI. In the case, let the time taken with T second. The time taken T second, what is the net heat supplied to water in T second? Net in water T second is this delta Q. That has to be equal to MC delta theta. That's what the equation is. So what is the heat supplied dQ in T second? dq here is 1000 joules minus 160 joules per second. That's the net rate at which heat is being supplied. Multiply by t second, that becomes my dq. Once I have my dq value, I equate to mc delta theta. Mass is also given, 2 liters. What will mass here? So when I use this one, what is the mass I'll substitute here? Moment I use this in joules, the right hand side also should be in similar unit. So mass should be in kg. So 2 liters is what? 2 liters is actually 2 kg. C will be in SI unit. C will also substitute equal to 4.2 into 10 to power 3 joules per kg. And then delta theta is given, temperatures from 27 to 77 into 50. I can easily get the value of T. So fairly simple question. Okay, let's look at one more here. The last question, I think it's almost time now. So a copper ball of 100 grams at temperature T. It is heated to certain temperature. It is dropped in a copper calorimeter of mass 100 grams. Filled with 170 grams of water. So it is something like this. If you have to understand what is a calorimeter, calorimeter is kind of basically a wooden box, insulated box. And it may also, you can imagine, it may have like wool coating or something. So you have felt or some other material so that it cannot transfer heat to the surrounding. And it has a vessel, normally keep a thin vessel, like a vessel of good conductor, normally copper, and it has certain water also. So what you've done here, so this forms a thermally isolated system. Copper ball temperature is dropped into copper calorimeter. This has a mass of 100 grams and is filled with 170 grams of water. So this is 170 grams of water, and there's a calorimeter also 100 grams, and a copper ball also dropped here. This copper ball which is dropped into this. So since earlier the copper ball and these are different temperature, of course heat transfer will take place, and finally it will come to an equilibrium temperature. Suppose the temperature is found to be 75 degrees centigrade. Okay, given room temperature, then a specific heat of copper also is given here. Okay, so what does the significance of room temperature of 30 degree mean? It means initial temperature of water and calorimeter also, initial temperature of water and calorimeter was 30 degree, and finally it has become 75 degree. So here copper ball will lose heat energy, calorimeter plus water will gain heat energy. Heat loss is equal to system is composed of 3 objects, copper ball, calorimeter, and water. Heat transfer equation, copper ball will lose energy and they will gain energy. Lose energy is initial temperature minus final temperature, 100 into specific heat capacity into change in temperature. And here, whenever you use calorie gram, mass also, everything you have to take in grams. That is only thing you need to be careful about. And this is equal to 100 grams per calorimeter, copper calorimeter. Simple substitution, 75 minus 30, 170 grams of water, 1 into 75 minus 30. Very easily can calculate T here. Okay. So in this case, there are 3 objects. What are this something? There is a copper ball and there's a calorimeter and water also. But many times in this is the calorimeter what we have for a certain calorimeter, the mass of the calorimeter is fixed and specific heat capacity also is known. So what we do many times, we write calorimeter of water equivalent of 10 grams kind of thing. So what does water equivalent of calorimeter mean? It means how many grams of water will have same heat capacity as calorimeter. So if I do so, what will be is water equivalent? Heat capacity of calorimeter is m into specific heat capacity. M is 100 grams, specific capacity is 0.1. And if I equate, m is the water equivalent, m into 1. So this will be equal to 10 grams of water. So same question could have been reworded. It dropped in a copper calorimeter of water equivalent of 10 grams. So what is the advantage of doing that one? If I say water equivalent to 10 grams, so I can treat even the calorimeter also water of 10 grams. I could take the total mass of water as 180 grams. That's just so rather than having 3 things coming into equation, it will have only 2 objects coming into equation. That's only significance of water equivalent. All right, so I'll stop here. I think this is almost time now.